Hey people, Notes 3.3b are on graphs of rational functions. And to be completely honest, in this video, we aren't really doing anything new. We're just kind of pulling everything together. So here are some things to do when graphing reciprocal or rational. This is better to say rational functions. Okay, so the first thing we want to do is factor and simplify as much as possible. And it's really important that we make sure to include any domain restrictions. So let's go ahead and do this first step right here. So when I factor the numerator, I'm going to use 2x and x. I want to get 15, so I will try 5 here and 3 here. And this gives me 3x, this gives me 10x. I can get a negative 7x if the 10 is negative and the 3 is positive, which means I will have a positive 3 here and a minus 5 there. The denominator is much easier to factor because of that leading coefficient of 1. So I will factor this as x minus 5 and x plus 1 right here. And then it says right here to factor and simplify. So we've done the factoring, but we need to simplify still. But before we do that, we know by looking at this that x is an element of the reals such that x cannot be 5 because I can't have 0 in the denominator, or negative 1. Okay, so when I simplify this right here, I can see that the x minus 5's cancel out. So I can say that f of x will behave like g of x, which is 2x plus 3 over x plus 1. Where did I get this? Well, there's a 2x plus 3 left over and an x plus 1 left over. Now, it behaves like it, but there is one thing that's different about g of x versus f of x, and we'll talk about that when we get to it, okay? All right, cool. So I factored and I've simplified as much as possible. So the next thing I want to do is determine any vertical asymptotes. So any vertical asymptotes are going to happen where I look at what's left over here and I see, are there any places here where x does not work? And it doesn't work when x equals negative 1. So I only have a vertical asymptote at x equals negative 1. So VA is going to be vertical asymptote. I'm going to say x equals negative 1. Now, why do I not have a vertical asymptote at x equals 5, even though there's a domain restriction right here? Because right here, there is no x minus 5 as a factor, and it behaves like this function right here. Let's take a look at f of x versus g of x. So we know that f of x is going to be 2x plus 3 times x minus 5 over x minus 5 times x plus 1. Now, let's take a look at what g of x looks like. So g of x is what we said it's going to behave like. So it's what we have here in f of x, except we are going to cancel out that x minus 5 that we have in common in the numerator and the denominator. We're going to divide it out. So right here, I would get 2x plus 3. And then in the denominator here, I get x plus 1. The x minus 5's divide out. And if you notice, they are exactly the same. And we do have that vertical asymptote at x equals negative 1. But if you notice right here, we do not have a vertical asymptote at x equals 5. Why is that? Because if you take a look at the function that f of x behaves like, there is no x minus 5 in that denominator. However, if we were to look at the original function, and if I were to go along the original function right here and just like pick just random points and see what happens, as I get closer and closer to 5, if you notice right here, it says that it's undefined. And if you notice, all of these other ones right here have dots until we get to this point right here. And now the circle becomes open. It was a closed circle before, now it's an open circle right here, because at 5, it's undefined. Whereas with this one right here, as I get closer and closer to 5, I actually have it in an actual value when x is 5, right? Like if you see here, it's not undefined there. So that is why we only have a vertical asymptote at x equals negative 1. So what does that tell me right here? So we've determined any vertical asymptotes. And if you notice right here, it says, let's just check this off. If you notice right here, it says where restrictions are that still remain in the denominator of the simplified fraction. So here, the only restriction that's left over is x cannot be negative 1. So that's where we would have our vertical asymptote. So then it says determine any points of discontinuity. And those are also known as holes, where restrictions are that have divided out in the simplified fraction. So if you see right here, the x minus 5 have divided out, so they're no longer in the simplified fraction because they've divided out. So that means that we're going to have a hole when x is 5. But I need to know the actual point that it's going to be. So I need to actually plug in 5. So I would go to f of 5 is equal to, and every time I see an x, I would plug in 5, right? So it would be 2 times 5 plus 3 times 5 minus 5 all over 5 minus 5 down here times 5 plus 1. I'm using this to plug it in, by the way, okay? So right here, 2 times 5 plus 3 is 10 plus 3, which is 13. 5 minus 5 is 0. 5 minus 5 right here is 0. And then 5 plus 1 is 6. So I end up getting 0 over 0, and that presents a problem for me because I don't know what this is. And this actually, we would normally say it's undefined if we have 0 in the denominator, but when it's 0 divided by 0, it's something different. It's actually called undetermined. Regardless, it doesn't make sense for me to plug this in to f of x. So when we're trying to find holes, plug the x value in to the simplified expression or the simplified function. We know that it behaves like this. So we know that it's going to be pretty much the same as this with a hole where x is 5. So I need to know, well, in g of x, what would the coordinate be? And then I would just place a hole there. So here would be g of 5 is equal to, so every time I see an x here, I'm just going to replace it with 5, which should be nice and easy because we already did that in the previous one, except we also had other factors here that we didn't have to deal with. So 2 times 5 is 10, 10 plus 3 is 13, and then 5 plus 1 is 6. So we know that our hole is going to be at 5 comma 13 over 6. And just a little heads up, just to help us out when we actually do our graph, 6 goes into 13 2 times with 1 left over, so it's 2 and 1 6. All right, so we've determined any points of discontinuity. We've determined all of our holes. So now we need to determine any horizontal or oblique asymptotes. Since the degree of our numerator is equal to the degree of our denominator, we're going to have a horizontal asymptote. So let's talk about this. Remember, horizontal asymptotes are pretty much your end behaviors, right? So what happens as x is getting infinitely large or infinitely positive and infinitely negative? So we're going to find the limit as x approaches infinity of 2x squared minus 7x minus 10 over x squared minus 4x minus 5. So when we're talking about super large numbers of x, right? We're talking about, like, for example, if I were to square 10,000, that would end up being 100 million. And this number is not even that big when we're talking about super massively large numbers. So 100 million is already, it's a pretty big number, right? But when you square a number, it's huge. When you square a large number, it becomes huge. So this stuff doesn't even matter. This stuff doesn't even matter. So this becomes the limit as x approaches infinity of 2x squared over x squared. The x squareds divide out, so I end up getting 2. So I would have a horizontal asymptote of y equals 2. And the same thing would happen on the left side of my graph, right? So if I were to approach negative infinity, this minus 7x minus 10 and this minus 4x minus 5 don't really matter when we're talking about super large values of x, or super negative values of x, super large negative values of x. So I get the limit as x approaches negative infinity of 2x squared over x squared, which is still 2. So I get y equals 2. And it would even work if I were to do it to the simplified fraction. So right here, when we had 2x plus 3 over x plus 1, The 3 and the 1 don't really matter right here. So the 3 doesn't matter, the 1 doesn't matter. So it's the limit as x approaches infinity of 2x over x, which would divide out to give us 2. So we'd still get y equals 2. And the same thing is true for as x approaches negative infinity. So here we can say that we have a horizontal asymptote at y equals 2. So we're done with our horizontal asymptote. You either have horizontal or oblique. There's no way that you could have both. So now determine the end behavior on both sides of each asymptote. So for this right here, I have end behavior on both sides of x equals -1, so to the left of it and to the right of it, and both sides of y equals 2, above it and below it. And I'll show you what I mean by that. But let's go ahead and graph out some information here first. So on the next page, let's get our graph set up. So I'm going to just put my x-axis right in the middle. And I'm also putting my y-axis right in the middle. I'm going to call this x, I'm going to call this y. I'm going to put 0 here, and I'm going to go by halves. So I'm going to say that every other number here is a whole. So 1, 2, 3, 4, 5, and then same thing on the other side. And then I'm going to do the same thing for my y values. And I'm going to go ahead and graph out my asymptotes. So we had a vertical asymptote at x equals -1. So I'm going to graph out a vertical asymptote right here. I'm going to graph out a vertical line. And I have a horizontal asymptote at y equals 2. So I'm going to graph this out right here. And I'm going to find the end behaviors around these asymptotes. But I'm actually going to skip that step first so I have a better picture of what's happening here. So the next step actually asks us to determine any x or y intercepts. So let's go ahead and do that right here. So we'll do this step right here. So for my x-intercept, just a reminder that your x-intercept will happen when y equals 0. So what I'm going to do is I'm going to set y equal to 0. So if f of x is going to equal to, I'm going to use the factored form, 2x plus 3 times x minus 5 over x minus 5 times x plus 1, then I would set that equal to 0, right? This is the y value. And then I would copy this down. So this 2x plus 3 times x minus 5 over x minus 5 times x plus 1. Now, whenever I set anything equal to 0, it's only the numerator that needs to be 0, right? 0 divided by anything will still always give me 0. I can't have 0 in the denominator because that it would be undefined. So I would just set the numerator equal to 0. So that means that x would have to equal -3 over 2 or +5. However, 5 was a restriction, so that's not going to work. So my x-intercept is just -3 over 2, 0. Now, just a quick heads up, I did a lot of extra work that I didn't really need to do for this question because here, I could just set this numerator equal to 0. So I could just literally set 2x plus 3 equals 0 and then solve for x there, and that would give me my x-intercept right here. So my x-intercept is -3 over 2, 0. -3 over 2 is exactly -1.5. So I will go to my graph and I will plot out the point -1.5 because that's going to help me out with my graph right here. Next thing that I want to do is find my y-intercept, and my y-intercept will happen when x equals 0. So same thing, I'm going to find f of 0. So here I have the option to plug it into the original function that we have right here. So every time I see an x, I'm going to replace it with 0. So if you notice here, all I'm doing is I'm just replacing the x value here with 0. So when I do that, I end up getting 2 times 0 is 0. Add 3 to that, I get 3. 0 minus 5 is -5, so it's 3 times -5 over 0 minus 5 is also -5 times 0 plus 1, which is 1. So I would end up getting -15 over -5, which is 3. So that means that my y-intercept would be at 0, 3. But just a reminder, it behaves like g of x, which is 2x plus 3 over x plus 1. So all I really have to do is find g of 0. So this would be 2 times 0 plus 3 all over 0 plus 1. And 2 times 0 is 0. Add 3 to it, I get 3. 0 plus 1 is 1. So I end up getting 3 over 1, which is still 3. Might be easier to use g of x because, again, it behaves exactly like g of x, except when x is 5. So here we know that our y-intercept will be at 0, 5. And then I can go, sorry, you have to flip back and forth. I can go to my graph and I can plot out the 0.05. So that's going to help me out a lot. I also have a hole at 5, comma, 2 and 1/6. So I also know that I have a hole. We figured out right here that this is going to be a hole here. So I'm going to go to 5, comma 13 and 2 and 1/6. So I'm also going to have a hole here. Now I need to see how my end behaviors are behaving. So you have a little bit of space underneath the intervals that we needed to fill in. So let's talk about our vertical asymptote. And our vertical asymptote is x equals -1. And I want to know what my end behavior is looking like here. So if I take a look at my graph, this is my vertical asymptote right here. I want to know, as I look at my vertical asymptote right here, as I get closer and closer to this asymptote, is my graph going down or is my graph going up? Okay, so that's what I want to figure out right here. So what I do is I have to test some numbers and see what happens when I test some numbers right here. But here's the other thing that we want to think about. X equals -1. I'm going to see what happens as I get closer to the vertical asymptote from the left side and then also from the right side. So here I want to know, as x approaches -1 from the left side, so this right here means the left side, what's y doing? What is y approaching? So what I'm going to do is I'm going to choose a number that's super, super, super close to
-1 on the left side. So I would use like -1.01. And then I could plug it into f of x or g of x. It doesn't matter, but I personally would prefer g of x because g of x is a lot easier. The reason why is because g of x is simpler, right? So I know that g of x, I'll just write it up here as just a reminder, is 2x plus 3 over x plus 1 right here. So I'm going to do 2 times -1.01 plus 3 over -1.01 plus 1.
So I will type in 2 times -1.01 plus 3, and I end up getting 0.98. So here I can say this is 0.98 over, and then -1.01 plus 1 is -0.01. When I divide that out, I end up getting -98. So I'm going to put it all into one fraction. So here you can see, again, we get -98. What does this -98 mean? It means that the number that we are approaching is a negative, somewhat large number. So if I make this even closer to -1, so maybe make this 0.000001. If you notice here, this number is even larger. This number is almost -1 million. So the closer I get to 0, the closer this, or the larger this number gets, but in the negative. One from, as x approaches -1 from the left side, y is going to approach -infinity, okay? And then I'm going to do the same thing for as x approaches -1 from the right side. So this means the right side. What's going to happen? What's y going to approach? So now I'm going to do g of a number that's super close to -1 from the right side, so -0.99. So I could do 2 times -0.99 plus 3 over -0.99 plus 1. So let's see what we get when I do that. So I'm just going to put it all into one fraction. And here we get 102. So this time we get a large positive number. And the closer I get to -1, the higher my value gets. I get 1,000,002 here. So this is telling us, so I'll say this is 102. So what this is telling us is that as x is approaching -1 from the right side, y is approaching positive infinity. So let's split this up. Let's talk about our vertical asymptote first. X equals -1. I'm going to zoom in so you can see what I'm talking about. So here we're going to say, as x approaches -1 from the left side, y approaches -infinity. And as x approaches -1 from the right side, y approaches +infinity. So if you take a look right here, what does that mean? As x approaches -1 from the left side, y approaches -infinity. That means that this is going to be going down to -infinity. And if you notice, it makes sense because that's where our x-intercept is. And as x is approaching -1 from the right side, y is approaching +infinity. So it's going to look something like this. But we'll do a better job of drawing this out shortly. So now let's see what's happening with our horizontal asymptote, which is y equals 2. So here we're going to see what happens for the end behaviors. So what's happening as we go farther to the right or farther to the left. So we're talking about really large values of x now in the positive side and on the negative side. So here we're going to say, as x approaches +infinity, what is y going to do? What's y going to approach? Well, we know y is going to approach 2, but we need to be more specific about what's happening here. So I'm going to test a really large number of x. So this, just a note right here, this is close to -1. And this is also close to -1. Here we're going to test large values of x, because again, we're talking about end behavior. So I'm going to choose a really large value of x. Maybe I will try 100, for example. So here I'm going to do 2 times 100 plus 3 over 100 plus 1. Again, using g of x right here. So I end up getting 203 divided by 101. Let's see what that gives us. So this right here gives me 2, pretty close to 2, but this number is slightly above 2, which would make sense, which should make sense to you, because 203 is more than double 101, slightly more than double 101. So I get 2.01. So here I'm going to say that this is going to be equal to 2.01, which means that it is approaching 2 from above, because 2.01 is higher than 2. So we say here that it's approaching 2 from above. Now I want to know what's going to happen on the left side of my graph. So as x is approaching -infinity, we still know y is going to approach 2, but is it going to approach it from above or underneath? So again, we're going to test a large number, but now we're going to test a large negative number. So here I'm going to say 2 times -100 plus 3 all over -100 plus 1. So I get -197 over -99. Let's see what this gives us. So -197 divided by -99 gives me a number that's really, really, really close to 2, but now it's less than 2. So we would say it's 1.99. So this means that it is approaching 2 from below. So we can say that this is approaching 2 from below. That's what this notation right here means. This means from below, and this means from above. Okay, so let's write this out. So for my horizontal asymptote, which is y equals 2, we can say as x is approaching +infinity, y is approaching 2 from above, and as x is approaching -infinity, y is approaching 2 from below. When we chose 100, this is the value that we got. The larger my x value is, the closer this gets to 2, but it's still bigger than 2. And the same thing is true for my negative x value. So we plugged in -100 plus 3 all over -100 plus 1. So this is close to 2, but it's under it. The closer I get, or the larger my value is right here, the closer I get to 2, but it's still approaching it from underneath. So, and then lastly, it says, so we're done with that. If necessary, find a few extra coordinates to paint the complete picture. I think that we have a good idea of what's going on here. So right here, because this is saying that as x is approaching negative infinity, y is approaching 2 from underneath. That means that on the left side, as we are approaching negative infinity, y is approaching 2 from underneath versus from above 2. And we also know that x is approaching -1 from the left side, y is approaching negative infinity. So we know that this right here will look as follows. Notice I was able to go through my x-intercept. So this piece right here is saying as x approaches negative infinity, y is approaching 2 from underneath. And then this piece right here is saying as x approaches -1 from the left side, y is approaching negative infinity. Okay, now let's look at the right side. We know on the right side that as x approaches -1 from the right side, y approaches positive infinity. And we also know that this is going through, I'm going to extend this a little bit, the point 0, 5. So we know that this right here is going to look like this right here. Okay, and then we also know that it's going to go through this hole right here. We just found out this hole right here, but we also know that as x approaches infinity, y is going to approach 2 from above, which it's doing. It's from above and not from below. Okay, so now we can go ahead and do our positive negative intervals and our increasing decreasing intervals. So I can see right here that my graph is positive from negative infinity all the way until my x-intercept, which is -3/2. And it does not include -3/2. And we can also say that it is positive from -1, from this point right here, all the way to infinity. We can see here that our graph is negative from this x-intercept here until -1. So it's only negative for a very small x interval. So from -3/2 to -1. And that's it. That's the only time it's negative. Now, if you notice, if I go from left to right, my graph is always decreasing. It is never increasing. So there are no increasing intervals in this example here. And for decreasing intervals, we can say that it is decreasing from negative infinity to my asymptote, so to -1. Then it's decreasing again from -1 until my hole, which is at 5. And then after that hole, it increases. It's decreasing from 5 to infinity. So pretty much it's always decreasing. However, we cannot say from negative infinity to positive infinity because we have points that are undefined in our graph. And that's it for this video. Make sure to ask any questions. Otherwise, we will see you in class. Bye.